Yes. Well, so in my last class, I have discussed about reflection of plane wave, normal incidence, right? So reflection of plane wave. Just a minute. So reflection of plane wave. What is meant by reflection of plane wave? So whenever EM wave incidents on a boundary, in general, part of the wave transmits and part of the wave reflects back, and that is called as reflection of plane wave. The instance of wave will be in two ways. One is normal, and another one is oblique instance, right? So normal instance and oblique instance. So when EM wave incidents normally, it is called as normal incidence. When EM wave incidents with some angle, when EM wave incidents with some angle, it is called as oblique instance. And we have been discussing on normal instance, right? So this is the boundary here. At z is equal to 0 is the boundary, and I'm assuming that the wave is propagating in z direction. When the wave is propagating in z direction, and the boundary is at z is equal to 0, boundary is at z is equal to 0, we can represent the instant wave, reflected wave, and the transmitted wave like this, as shown in figure. Instant wave. So instant wave, which consists of instant electric field and instant magnetic field. And as I said, AK bar indicates the direction of wave propagation, and EI is the instant electric field, HI is the instant magnetic field. And part of the wave reflects. ER is the reflected electric field, HR is the reflected magnetic field, and part of the wave transmits, and ET is the transmitted electric field, and HT is the transmitted magnetic field. So here, the direction of electric field and magnetic field for instant wave and the transmitted wave, they are the same, right? The direction of electric field for both instant and transmitted waves, it is the same, and for magnetic field also, right? The directions will not changes for instant and transmitted wave. But whereas reflected wave, the direction of magnetic field changes, and the direction of wave propagation also changes. They will be reversed. Yeah, so that is how we can represent waves, right? And we have written instant waves, right? So instant wave is in this form: instant electric field and instant magnetic field, equation 1 and equation 2. And reflected waves, equation 3 and equation 4. And transmitted waves, equation 5 and equation 6 are the transmitted waves. And we have noticed from the figure that the total field in region 1 is the sum of incident waves and reflected waves, right? The total fields in region 1 is the sum of instant and reflected waves, right? So therefore in region 1, right, um, total electric field is EI plus ER, and total magnetic field is HI plus HR. And similarly, in region 2, the total electric field is the transmitted electric field, and the total magnetic field is transmitted magnetic field. And from the boundary conditions, right? So boundary conditions requires that and the tangential component is continuous. So tangential component is continuous in the sense when wave travels from one region to the another region, there will not be any change in the tangential component of electric field. There may be changes in normal component of electric field, but there are no changes in the tangential component of electric field or magnetic field, right? So in my last class I have explained what is tangential component and what is normal component, that I have explained. So therefore applying boundary conditions will get E1 is equal to E2 and H1 is equal to H2, right? So that means the total electric field in region 1 is equal to the total electric field in region 2. Similarly, the total magnetic field in region 1 is equal to the total magnetic field in region 2, and this is only at the boundary, right? So please make a note of it. This is at the boundary, not somewhere else. Only at the boundary. That means at z is equal to 0, right? Only at z is equal to 0, electric field and magnetic fields are equal, right? Tangential components are equal. So therefore, equating will get equation 7 and equation 8, right? And EI, ER, and ET you can get from equations 1, 3, and 5, right? So from equations 1, 3, and 5, substituting in equation 7, we will get equation 9 like this. And similarly, equation 8, HI, HR, HT, from equations 2, 4, and 6, substituting in equation 8, and we'll get equation 10, right? So equation 9 and equation 10 at the boundary, right? At the boundary means at z is equal to 0. So substituting z is equal to 0, we will get equation 11 and equation 12, right? Equation 11 and equation 12 we will get. And solving equation 11 and equation 12, we will get reflection coefficient and transmission coefficient, right? So what is meant by reflection coefficient? Reflection coefficient is the ratio between ER by EI. That means reflected wave to the instant wave, right? So from this we can write reflected electric field is equal to reflection coefficient into the instant electric field, right? So this is the relationship between ER and EI node, right? So therefore, reflected wave can be calculated. If we know reflection coefficient, we can determine reflected wave, reflected electric field we can calculate. And similarly, transmission coefficient. So transmission coefficient is the ratio between transmitted wave to the instant wave. Reflection coefficient is ratio between reflected wave to the instant wave. Transmission coefficient is the ratio between transmitted wave to the instant wave. And solving equations 11 and 12, and we'll get this one, right? So reflection coefficient eta 2 minus eta 1 by eta 2 plus eta 1, and transmission coefficient 2 eta 2 by eta 1 plus eta 2, right? So coming to the characteristics, of reflection coefficient and transmission coefficient. Well, let us see some characteristics. Just a minute. right? So welcome back. So coming to the characteristics, of reflection coefficient and transmission coefficient. Number one, 1 plus reflection coefficient is equal to transmission coefficient, right? 1 plus reflection coefficient is equal to transmission coefficient. So 1 plus reflection coefficient. So what is reflection coefficient? Eta 2 minus eta 1 by eta 2 plus eta 1. So this is equal to, if you simplify this, eta 2 plus eta 1 minus eta 2 minus eta 1 divided by eta 2 plus eta 1. So this is equal to 2 eta 2 by eta 1 plus eta 2, right? So therefore 1 plus reflection coefficient is equal to transmission coefficient. And so that is the first characteristics of this. And both reflection coefficient and transmission coefficient are dimensionless, right? Both are dimensionless because they are the ratios, right? Electric field to the electric field, right? So they are the ratio. So therefore, both are dimensionless. And third one, the reflection coefficient. The reflection coefficient is always in between 0 and 1, right? Reflection coefficient, magnitude of reflection coefficient is always in between 0 and 1, right? So these are the characteristics of reflection coefficient and the transmission coefficient, right? So now let us consider case 1, right? Let us consider case 1, right? Let us assume that region 1 is a perfect dielectric, and region 2 is a perfect conductor, right? Region 1 is a perfect dielectric and region 2 is a perfect conductor. So here the derivation is derived by considering general case, right? So general case in the sense, this is region 1 and this is region 2, right? But we don't know what is region 1 and what is region 2, right? Region 1 may be anything. It may be free space, dielectric, or conductor. And similarly, region 2, it may be free space, dielectric, or conductor, whatever the region may be, right? So irrespective of the region, we have determined reflection coefficient and transmission coefficient, the expressions for reflection coefficient and transmission coefficient, right? So now let us assume that region 1 is a perfect dielectric and region 2 is a perfect conductor, right? Region 1 is a perfect dielectric and region 1 is a perfect conductor, right? So perfect dielectric in the sense, you can take lossless dielectric media, right? So for lossless dielectric media, um, um, uh, what we can write, sigma. What are the characteristics? Perfect dielectric. What are the characteristics you have? Sigma is equal to region 1, right? Sigma 1 is equal to 0, mu 1 is equal to mu r1 and mu naught, and epsilon 1 is equal to epsilon r1 epsilon naught, right? These are the characteristics. And for perfect conductor, region 2, sigma 2 is equal to infinite and epsilon is equal to epsilon naught, epsilon 2 is equal to epsilon naught, mu 2 is equal to mu r2 mu naught, and sigma 2 is very much greater than omega epsilon, right? So these are the characteristics for a perfect conductor. Perfect conductor in the sense good conductor. Once let me verify the characteristics. I have a small doubt. Yes, so these are the characteristics. So good conductor and lossless dielectric media. So these are the characteristics, right? And now reflection coefficient and transmission coefficient. Reflection coefficient. What is reflection coefficient? Is equal to eta 2 minus eta 1 by eta 2 plus eta 1, and transmission coefficient is 2 eta 2 by eta 1 plus eta 2. Right? So these are the transmission coefficients, where where what is eta 1? Eta 1 is intrinsic impedance, right? So therefore intrinsic impedance root over j omega mu 2 divided, sorry, j omega mu 1 divided by sigma 1 plus j omega epsilon 1, and similarly eta 2 is equal to root over j omega mu 2 divided by sigma 2 plus j omega epsilon, right? So this is the expression for the intrinsic impedance. If you go back, um, um, somewhere else I have derived this equation, right? So let me show it here, right? It's intrinsic impedance. So the derivation I have done earlier. So what is the expression? Yes. So this is the intrinsic impedance. Eta is equal to root over j omega mu by sigma plus j omega epsilon, right? So this is the expression. I have taken this expression here, right? So C eta 1 is equal to root over j omega mu 1, and eta 2 is equal to root over j omega mu 2 by sigma 2 plus j omega epsilon. Now substitute the characteristics here. So eta 1 is equal to what will get? Root over mu 1 by epsilon 1, and eta 2 is equal to 0, right? Eta 2 is equal to 0. So why eta 2 is equal to 0? Since sigma 2 is infinite, right? Region 2 is a perfect conductor. So therefore, sigma 2, the conductivity is infinite. So therefore, intrinsic impedance is 0, right? So if it, so that means what? Eta 1 not equal to 0, eta 2 is 0, right? So if you substitute these values here, so eta 2 is equal to 0, and you will get reflection coefficient -1, right? Reflection coefficient -1, and transmission coefficient. So what is transmission coefficient? Eta 2 is 0. So therefore, transmission coefficient is 0, right? Transmission coefficient is 0, right? So this is for what? When region 1 is a perfect dielectric and region 2 is a perfect conductor, right? So when region 2 is a perfect conductor, transmission coefficient is 0. So what is meant by transmission coefficient is 0? Transmission coefficient is 0 in the sense none of the wave transmits, right? None of the wave transmits. Reflection coefficient is -1 in the sense what? So what is reflection coefficient? Reflection coefficient is equal to, it is the ratio between reflected wave to the incident wave, right? Reflected wave to the instant wave, and this is equal to -1, right? So this implies ER is equal to minus EI, right? ER is equal to minus EI, right? So that means what? The EI is instant wave and ER is reflected wave. So therefore, the entire wave reflects back, right? The entire wave reflects back with opposite phase, with phase reversal, minus, right? Minus sign indicates that the electric field reflects back with phase reversal, right? So for example, here let us say this is the boundary which we have, right? So this is the boundary, right? So region 1, so region 1 is a dielectric, perfect dielectric, and region 2 is a conductor, right? Region 2 is a conductor, right? So where eta 2 is equal to 0, right? Eta 2 is equal to 0, and eta 1 not equal to 0 here, region 1, right? So in this case, a reflection coefficient, right, is minus 1. That means what? The entire wave reflects back, right? The entire wave reflects back. So let us say this is the incident wave, right? This is the incident wave, right? So reflection coefficient is minus 1, right? Minus 1 means like this. So the entire wave reflects back. And this one is, sorry, this one is reflected wave, right? So the entire wave reflects back, right? The entire wave reflects back, right? And with phase reversal at the boundary at z is equal to 0. So this is the boundary. So at the boundary, phase reversal, right? Phase reversal. So this is the ER is equal to minus ER, right? ER is equal to minus ER, and none of the wave transmits, right? None of the wave transmits. It's because transmission coefficient is 0, right? Transmission coefficient is 0, so therefore none of the wave enters into region 2, right? So instead the entire wave reflects back, right? So this is about reflection of plane wave normal instance, right? So is it clear to you? Related problems. Let us do one small problem. Problem 1. In free space, that is z less than or equal to 0, a plane wave with h is equal to 10 cos 10 power 80 minus beta z ax bar milliampere per meter is incident normally on a lossless medium, on a lossless medium, um, with epsilon is equal to 2 epsilon naught, mu is equal to 8 mu naught in a region z greater than or equal to 0. Determine the reflected wave, reflected waves, and and the transmitted waves, right? So this is the problem. Very simple. The problem may looks bigger, but the procedure is very simple, right? So once read out the problem. So read the problem and understand what we have to determine. Then 50% answer is over, right? So understanding problem itself, 50% you are through, right? So here, first of all, identify the boundary. What type of boundary is this, right? So we have a boundary, right? So this is the boundary at z is equal to 0. So this is region 1, z less than or equal to 0, and this is region 2, z greater than or equal to 0, right? Region 1 and region 2. What is region 1? Region 1 is free space, right? It was given in the problem in free space. And region 2, so what is region 2? Is lossless media, right? So region 2 is lossless dielectric, right? Medium 2 is lossless dielectric. And what are the values here given? To epsilon naught, and mu is equal to 8 mu naught, right? So mu 2 epsilon 2, right? Because region 2 mu 2 epsilon 2, right? Anything else we have? Yes, right? So this is the boundary, right? So a boundary between free space and lossless dielectric media. Free space. For free space, what else you know? For free space, what else you know? Sigma 1 is 0 for free space, and mu 1 is equal to mu naught, and epsilon 1 is equal to epsilon naught, right? For free space, these are the characteristics which we know, right? Um, and here epsilon 2 is equal to epsilon r1 epsilon naught, right? So therefore epsilon r1 is 2, and sorry, mu epsilon r2 is 2, and mu r2 is 8, right? Mu r2 is, since epsilon 2 is equal to epsilon r2 epsilon naught, and mu 2 is equal to mu r2 mu naught, right? So these are the things which we know here. And one more thing, here 10 cos 10 power 80, right? 10 power 80, that means what? Omega is equal to 10 power 8, right? So in fact, this is in this form: h is equal to h naught cos omega t minus beta z ax bar, right? So this is in this form. So therefore omega is 10 power 8, right? So this is what the data we know, right, regarding the problem. This is what the data, whatever the available data we have. So this one, right? So from this, let us try to do the problem. So what we need to determine reflected waves, right? Determine reflected waves and transmitted waves, right? And and one more thing, h bar is incident normally, right? H bar is incident normally. So therefore incident magnetic field is given hi, right? Hi bar is equal to 10 cos 10 power 8t minus beta z, and which is in x direction, right? So this is given. Let us say this is equation 1, and we need to determine reflected waves. What is meant by reflected waves? Reflected waves. Reflected wave means ER and HR. Transmitted waves. Transmitted waves. So transmitted waves means ET bar and HT bar, right? So we need to determine these parameters, right? And hi, equation 1 is hi, therefore beta 1, right? Beta 1. Why beta 1? Because instant wave is in region 1. Instant wave belongs to region 1. Reflected wave also belongs to region 1. Transmitted wave belongs to region 2, right? So therefore beta 1, so we can calculate beta 1. So beta 1 is equal to, so what is beta 1? Omega by v, v naught, free space, right? Beta 1 is equal to omega by v naught. So what is omega? 10 power 8 divided by 3 into 10 power 8. So which is equal to 1 by 3, right? Beta 1 is 1 by 3, and beta 2, so beta 2 also we can determine omega by v, right? Beta 2 is equal to omega by v. It is not v naught, right? Because region 1 is free space, whereas region 2 it is not free space, right? V2, right? Beta 2 is equal to omega by v2, right? Where v2 is equal to 1 by root mu 2 epsilon 2, and this is equal to 1 by root mu 2. So what is mu 2? 8 mu naught into epsilon 2. Epsilon 2 is 2 epsilon naught, right? So this is equal to 3 into 10 power 8 divided by 4, right? So here in the denominator, um, 8 2s are 16, so 4, right? And 1 by root here, since 1 by root mu naught epsilon naught is equal to 3 into 10 power 8, right? So therefore v2 is this one, right? So substitute v2 here. So substituting v2 here, we will get beta 2. What is beta 2? Beta means phase constant, right? So 10 power 8 divided by 3 by 4 into 10 power 8, and this is equal to 4 by 3, right? Beta 2 is 4 by 3, right? And now, um, from equation 1 hi. If we know hi, we can determine ei, right? If we know hi, we can determine ei. How we know that, right? We know that um, e by h is equal to eta. Therefore ei by hi is equal to eta 1, right? Because instant wave is in region 1, therefore eta 1, right? So therefore ei is equal to eta 1 hi, right? Eta 1 hi. And what is eta 1? What is eta 1? So here let us determine eta 1 also here, right? So eta 1, so eta 1 is equal to root over j omega mu 1 by sigma 1 plus j omega epsilon 1. So this is equal to root over mu naught by epsilon naught, and this is equal to 125. And similarly, eta 2. So eta 2 is equal to root over j omega mu 2 divided by sigma 2 plus j omega epsilon 2, right? So uh, sigma 2 is 0, right? So because lossless. For a lossless, sigma 2 is equal to 0. For free space also, sigma is 0, right? So therefore, eta 2 is equal to root over mu 2 by epsilon 2. And this is equal to root over 8 mu naught divided by 2 epsilon naught, right? 2 epsilon naught. And this is equal to how much you'll get? 240 pi, right? You'll get 240 pi. So eta 1 is 120 pi and eta 2 is 240 pi. You'll get, right? Is it right? Am I doing right? Yes, right? So you'll get this one, right? So this is how we can calculate that, right? So therefore ei is equal to eta 1, right? Eta 1 is 120 pi and hi. So what is hi? Hi is equal to 10 cos, hi is equal to 10 cos 10 power 80 minus beta 1 z. Here what is the direction? Ax bar, right? So Ax bar, right? So is it true? Can I write like this directly hi? Can I substitute hi directly like this? No. Why? What is the contradiction here? What is the direction of ei? The direction of ei is ax bar. And what is the direction of magnetic field here? The direction of magnetic field is ax bar, right? So if you substitute hi directly, right? If you substitute hi directly here, you will get electric field direction also same, right? But it is a contradiction. So therefore, while using this expression, right? While using this expression, you should not substitute the direction of magnetic field directly, right? You should not substitute the direction of magnetic field directly. You need to calculate the direction of magnetic field. How you can calculate? We know that ae bar cross ah bar is equal to ak bar, right? So we don't know what is ae bar, and ah bar we know because it was given, right? It was given in the problem. So h bar, the direction of magnetic field is ax bar, right? Direction of magnetic field is ax bar. And what is the direction of wave propagation? The direction of wave propagation is here minus beta 1 z, right? Minus beta 1 z. So minus beta 1 z in the sense what? Minus z. Minus z in the sense the wave is propagating in positive z direction, right? The wave is propagating in positive z direction. So therefore, AK bar is AZ bar, right? So AE bar cross AX bar is equal to AZ bar. Therefore, AE bar, what is AE bar? AE bar is equal to minus AY bar, right? According to this equation, AE bar should be minus AY bar. Then only this expression will get satisfied, right? So to satisfy this equation, to satisfy this equation, AE bar should be minus AY bar, right? So therefore EI bar is equal to, right? EI bar is equal to um, 120 pi into 10. So 1200 pi cos 10 power 80 minus beta 1z minus AY bar, right? Minus AY bar. And let us say this is equation 2, right? So therefore, if we know HI, right? If we know HI, we can determine EI, right? EI like this, right? So now we need to determine reflected waves and instant waves, transmitted waves, right? So how we can determine reflected waves and instant wave? We know that reflection coefficient is equal to ER by EI, and transmission coefficient is equal to ET by EI, right? So we know EI. So if we know EI from this, right, from this we can determine ER. ER is equal to reflection coefficient multiplied by EI, and similarly ET is equal to transmission coefficient multiplied by EI, right? Let us say this is equation 3 and this is equation 4, right? Therefore, substitute equation 2 here, and similarly substitute this equation here, right? Here, and simplify it, right? Simplify, you will get ER and ET, right? ER and ET. So once we know ER and ET, we can determine HR and HT, right? How we can determine HR and HT? We know that ER by HR is equal to eta 1, and ET by HT is equal to eta 2, right? Because transmitted wave means in region 2, right? So therefore, HR is equal to ER by eta 1, and HT is equal to ET by eta 1, right? So this is how we can determine HR, uh, and this is how we can determine HT if we know ER and ET. If we know electric field components, we can determine magnetic field components, right? So as I said, whenever you use this relation, right? Whenever you use this relation, you need to take care about the direction, right? You need to take care about the direction. So this is how we can do the problem, right? So in the next class, I will complete the problem, right? Don't worry. Um, as the time is up, let us close the session here, right? So thank you very much for your patient listening. Just a minute, let me close the streaming.